What if everything we think we know about the universe's expansion is based on a cosmic misunderstanding? For decades, astronomers have been captivated and at times confounded by the idea of dark energy, an invisible force pushing our universe apart at an accelerating rate. It's one of the greatest mysteries in modern science, accounting for nearly 70% of everything in existence, yet it has never been directly observed or fully explained. But what if dark energy isn't what it seems? What if, instead of some exotic, unknown substance, it's actually the lingering echo of events that unfolded eons ago, the faint signature of ancient cosmic cycles repeating across unimaginable spans of time? That's the provocative possibility we're exploring today, an idea that challenges not just what we see through our telescopes, but how we understand the very fabric of reality. Imagine a universe that doesn't simply expand from a single beginning toward an uncertain end, but one that breathes, cycles, and renews itself across ages. In such a cosmos, what appears to us as dark energy could be something far more profound, a relic, a memory, a kind of celestial fingerprint left behind by universes that came before our own. This isn't just science fiction, it's a compelling, mathematically grounded alternative that more and more physicists are taking seriously. In this video, we'll journey through 21 distinct reasons why dark energy might not be a fundamental force at all, but rather a misunderstood byproduct of these vast cosmic rhythms. We'll start with the historical discovery that shook astronomy to its core, move through puzzling anomalies in the cosmic microwave background, and the growing tension in how we measure the universe's expansion, and venture all the way to predictions from string theory, quantum gravity, and simulations of cyclic cosmologies. Each piece of evidence builds on the last, painting a picture that's both astonishing and deeply elegant, one that could reshape our understanding of time, space, and our place in the cosmos. So settle in, open your mind, and join me as we explore one of the most thrilling possibilities in modern astrophysics. That dark energy is not a mystery to be solved, but a story to be remembered. To truly grasp why this idea of dark energy as a cosmic echo is so revolutionary, we need to rewind the clock and revisit the moment it was first proposed. The year was 1998, and two independent teams of astronomers were engaged in a seemingly straightforward task: measuring the universe's expansion by studying distant stellar explosions known as Type 1, a supernova. These supernovae are vital cosmic tools because they act as standard candles. Their known, consistent brightness allows scientists to calculate their distance with remarkable precision. The prevailing assumption across the entire field of cosmology was that the gravitational pull of all the matter in the cosmos was gradually slowing down the expansion that began with the Big Bang. Everyone expected to see a universe gradually applying the brakes. What they found instead sent a shockwave through the scientific world. The data revealed something utterly confounding. The most distant, and therefore oldest, supernovae were actually fainter than their predicted brightness suggested they should be. This meant they were farther away than anyone had calculated. The only possible explanation was that the expansion of the universe wasn't slowing down at all. In fact, it was speeding up. Some unknown, repulsive force was actively pushing galaxies apart at an ever-increasing rate, fighting against the relentless pull of gravity. This was akin to tossing a ball into the air and watching it not only fail to fall back down, but instead hurtle away from you faster and faster into the sky. It defied all conventional logic. This discovery was so radical and so unexpected that the researchers themselves were deeply skeptical. scrambling to rule out any potential errors, from interstellar dust dimming the light to intrinsic variations in the supernova themselves. But the evidence was robust and undeniable. The universe was accelerating. For this work, team leaders Saul Perlmutter, Brian Schmidt, and Adam Rees would later be awarded the Nobel Prize in Physics in 2011. The scientific community had to accept a new, bizarre reality. A mysterious component, soon dubbed dark energy, made up roughly 68% of the entire energy density of the cosmos, dominating its evolution and ultimate fate. Yet, from the very moment of its discovery, dark energy was a paradox. It was a label for an effect, not an understood substance. It had no direct detection, no known mechanism, and no place within the established standard model of particle physics. The most straightforward theoretical fit was Einstein's cosmological constant, a sort of energy inherent to the fabric of space itself. But the calculated value of this energy from quantum theory was astronomically, almost laughably, larger than what was observed, off by a factor of 1 followed by 120 zeros. This monumental fine-tuning problem, known as the cosmological constant problem, remains one of the greatest unsolved mysteries in physics. It's a gaping hole in our understanding, a clear sign that something fundamental is missing from the equation. This profound enigma is precisely what opens the door for alternative explanations. If dark energy doesn't make sense as a new, fundamental force, perhaps it isn't one. The historical context is crucial because it shows that dark energy was never a fully formed concept. It was an admission of ignorance, a placeholder for a phenomenon that defied explanation. This inherent mystery invites us to look beyond the standard model, to consider that the acceleration we measure today might not be driven by a strange new energy, but could instead be a lingering consequence of the universe's own deep history, a footprint left by processes we are only beginning to imagine. This idea of a universe that breathes in and out, expanding and contracting in a grand, rhythmic dance, is not a new one. In fact, it's a concept that has captivated human imagination for millennia, appearing in the spiritual texts and creation myths of ancient cultures from Hinduism to Buddhism, and even in the philosophies of the ancient Greeks. These traditions often spoke of vast days and nights of Brahma, or great years, cycles of creation and destruction spanning billions of years. Today, this poetic intuition is being reborn in the language of theoretical physics, not as mythology, but as a serious cosmological model that offers a powerful alternative to the standard story of a single, linear Big Bang. So what does a cyclic universe actually look like? Instead of a singular beginning from a point of infinite density, imagine a cosmos with no true start or end. In one popular modern rendition, our universe is a four-dimensional brain existing within a higher dimensional bulk. A collision between our brain and another could have sparked the hot, dense state we identify as the Big Bang, but that wouldn't be the absolute beginning. It would just be the latest reset, the most recent turning of the page in an infinite cosmic story. After this collision, the universe expands and cools much as we observe, forming galaxies, stars, and planets. But then, rather than expanding forever into a cold, dark emptiness driven by dark energy, the cycle eventually reverses. After trillions of years, the expansion slows, stops, and a gradual contraction begins, gathering all matter and energy back together in a big crunch that sets the stage for the next collision, the next bang, and the next cycle. Now, here's where the connection to dark energy becomes absolutely fascinating. Each of these cycles isn't a perfect, identical repetition. Information, in some form, might be preserved. Think of it like a cosmic game of telephone. Each universe inherits a faint whisper, a subtle imprint from the one that came before. This could be in the form of quantum fluctuations, gravitational waves, or even a kind of cosmological entropy, a memory of the structure and energy of the previous epoch. As the new universe begins its expansion, these residual imprints from the ancient past don't just vanish. They are woven into the very fabric of space-time itself. This is the crucial pivot in our thinking. What if the observed acceleration of our universe isn't being driven by a new, mysterious, dark energy force, but is instead a manifestation of this residual energy? The echo of that previous contraction, the momentum left over from the colossal rebound of the last big crunch, could be gently or even forcefully pushing our current universe apart. In this view, dark energy isn't an exotic substance we need to discover. It's a historical effect, a cosmic afterglow. It's the universe still feeling the effects of a monumental event that occurred in a cycle so long ago that its origin is all but invisible to us, leaving only its accelerating influence as a clue. This elegant idea reframes one of physics' biggest mysteries, not as a puzzle to be solved with new particles, but as a story to be read in the faint, ancient memories of the cosmos. To understand why these ancient light patterns might hold the key to rethinking dark energy, we first need to appreciate what the cosmic microwave background truly is. Picture the universe in its infancy, a mere 380,000 years after the Big Bang. Before this moment, the cosmos was an opaque, searing plasma, far too hot for light to travel freely. Protons and electrons were locked in a frantic dance, constantly scattering photons in every direction. But as the universe expanded and cooled, a monumental transition occurred. Those electrons and protons finally combined to form neutral hydrogen atoms, and in an instant, the universe became transparent. The light that had been trapped within that primordial soup was suddenly set free, and it has been traveling across the cosmos ever since, cooling and stretching with the expansion of space into the faint microwave glow we detect today. This is the CMB, not just an afterglow, but the very first baby picture of our universe, a snapshot of its condition at that critical moment of birth. When we map this radiation across the entire sky with satellites like Planck, we don't see a perfectly smooth, uniform blanket of light. Instead, we see a tapestry of incredibly subtle variations in temperature, tiny fluctuations, on the order of 1/100,000th of a degree. These anisotropies, as they're called, are the seeds of all future structure. The slightly denser, hotter spots would eventually, over billions of years, collapse under their own gravity to form the vast cosmic web of galaxies and galaxy clusters we see today. The standard model of cosmology, known as Lambda CDM, uses a specific recipe of ordinary matter, dark matter, and dark energy to predict the exact statistical pattern these fluctuations should form. For the most part, it works astonishingly well, but there are persistent, curious anomalies that act like stubborn pieces that don't quite fit the puzzle. Some of the largest scale fluctuations appear weaker than the model says they should be. There's a mysterious cold spot in the southern sky that is difficult to explain, and certain alignments in the data, often whimsically called the axis of evil, seem to suggest a preferred direction in the universe, which directly contradicts the fundamental assumption that the cosmos is isotropic, or the same in all directions. According to the standard model, these features are just statistical flukes, cosmic noise in an otherwise clear signal. But what if they're not flukes? What if they are actually important clues? This is where the concept of cosmic cycles re-enters the picture with a compelling alternative explanation. In a cyclic universe, each new cycle isn't born from nothing. It's reborn from the ashes of the previous one. The process of a big crunch and subsequent bounce wouldn't erase everything. Just as a lake's surface remains disturbed long after a stone has been thrown in, the fabric of space-time could retain imprints or memories from the universe that came before. The quantum fluctuations that seeded structure in the previous cycle might leave a faint residual signature that gets imprinted onto the new CMB of the next universe. The anomalies we see, those unexpected cold spots, odd alignments, and suppressed large-scale fluctuations, could be the faint, ghostly fingerprints of structures that existed in a prior cosmic epoch. They are not random noise, they are cosmic archaeology, evidence of a history that predates our own Big Bang. Now connect this directly to the mystery of dark energy. In the Lambda CDM model, dark energy is a smooth, uniform force that acts equally in all directions to drive acceleration. But if the primordial seed fluctuations we see in the CMB already contain these anomalous, directional imprints from a previous cycle, then the evolution of the universe would be subtly different from the very start. The way structures form and the way expansion proceeds would be influenced by this embedded memory. The effect we attribute to a mysterious, repulsive dark energy could actually be the result of this inherited momentum or residual energy from the cyclic rebound. The acceleration isn't being caused by a new force, it's the continuation of a motion that began in a previous cosmic phase. The anisotropies are the hint that our universe's initial conditions were not pristine and simple, but complex and inherited, challenging us to see dark energy not as a fundamental ingredient but as a dramatic echo of a forgotten past. Now, if the anomalies in the cosmic microwave background are the first crack in the foundation of our standard model, then the Hubble tension is a full-blown quake threatening to bring the entire structure down. This isn't a subtle statistical oddity. It's a direct, stubborn, and growing conflict between two of the most trusted methods we have for measuring the universe's expansion rate, a value known as the Hubble constant. On one side, we have what's called the local distance ladder approach. This is a meticulous, step-by-step process where astronomers use incredibly reliable celestial markers like Cepheid variable stars and those same type 1 a supernova that discovered dark energy to measure distances to relatively nearby galaxies. By observing how fast these galaxies are moving away from us and knowing their distance, we can calculate the current expansion rate with impressive precision. This local measurement gives us a value of about 73 kilometers per second per megaparsec. On the other side of this cosmic courtroom, we have the early universe probe. This method uses the pristine snapshot of the infant cosmos, the Planck satellite's map of the cosmic microwave background we just discussed. By assuming the standard Lambda CDM model is correct, including a specific, constant behavior for dark energy, scientists can run the cosmic movie backwards from that baby picture to predict what the expansion rate should be today. This method is just as rigorous and yields a value of around 67 kilometers per second per megaparsec. The problem is stark. These two numbers, each backed by overwhelming evidence and painstaking work, do not agree. They are separated by a gap that cannot be explained away by measurement errors or random chance. This is the Hubble tension, and it represents a fundamental crisis in cosmology, suggesting that something is seriously wrong with our understanding of the universe's ingredients or the laws that govern them. The standard response has been to try and tweak the Lambda CDM model, perhaps by suggesting that dark energy's strength isn't constant after all. Maybe it has evolved over time, getting stronger or weaker in a way our simple models didn't account for. But these modifications often feel like patches, creating new problems even as they try to solve this one. This is where the cyclic universe model strides in with a far more elegant and natural explanation. Remember, in a cyclic cosmos, the dark energy effect isn't a fundamental constant. It's a transient phenomenon, a leftover influence from a previous cycle. It's not a steady push but a fading echo. This means its strength would naturally change over the history of our universe. It might have been stronger in the past or could be weakening now, a dynamic behavior that is built directly into the model's core premise, not added as an afterthought. If the repulsive force we call dark energy has been variable, it would completely reshape the interpretation of our measurements. The Planck data from the early universe would be sensing the effect of this force at a different strength than what our local measurements are detecting today. The tension isn't a sign that one team is wrong. It's a clue that the force itself is not what we thought it was. The cyclic model doesn't just accommodate this variance, it predicts it. The Hubble tension, therefore, transforms from a confusing problem into a potential smoking gun. It could be the first direct evidence that the acceleration we see is not driven by a static, mysterious energy, but is instead the dissipating reverberation of an ancient cosmic event, a final sigh from a universe that existed long before our own. But the story of cosmic structure doesn't end with the initial seeds revealed in the CMB. Over billions of years, those tiny fluctuations in density were amplified by gravity, eventually giving rise to the magnificent and intricate cosmic web we observe today, a vast network of galaxy clusters, long filaments of dark matter, and enormous empty voids. This is the universe's large-scale structure, and it holds another set of profound clues that challenge the dark energy narrative. According to our most sophisticated computer simulations based on the standard Lambda CDM model, the gravitational pull of dark matter should have sculpted this web in a very specific way, with dark energy later acting as a sort of cosmic brake, slowing down the formation of new clusters and stretching the voids ever larger. For the most part, this simulation matches what we see, but there are intriguing and persistent deviations, subtle wrinkles in the fabric of the cosmos that suggest our model might be missing a key ingredient or perhaps misinterpreting one entirely. Some of the largest voids appear to be slightly too big and too empty. The clustering of galaxies on the very largest scales shows statistical patterns that are just a bit off from theoretical predictions. There are even hints of structures so immense, like the controversial Hercules Corona Borealis Great Wall, that they seem to challenge the fundamental principle that the universe should look roughly the same everywhere beyond a certain scale. While none of these anomalies are conclusive on their own, together they form a pattern of small discrepancies, a quiet but consistent background hum suggesting that the standard story of how gravity and dark energy built our cosmic home might be an oversimplification. This is where the cyclic universe model offers a radically different and perhaps more complete explanation for what we see. In a cyclic cosmos, the process of structure formation doesn't begin from a clean slate with our Big Bang. Instead, the new universe is born with a head start, inheriting a faint but real ghost of the large-scale structure from its predecessor. Imagine the universe not as a blank canvas but as one that has been painted over. The old image is mostly gone, but its underlying texture and some faint outlines still influence the new painting being created on top. This cosmic memory would manifest as residual energy or momentum woven into the fabric of space-time itself. As gravity begins its work of pulling matter together into the first protogalaxies, it's not just working with the quantum fluctuations from our inflation, it's also working with this inherited energy from a past cycle. This residual energy would act as a subtle pressure, influencing how quickly structures can collapse and how large the voids between them can grow. In many ways, its effect would be indistinguishable from the repulsive push we attribute to dark energy. It would resist the gravitational collapse of matter, suppressing the formation of some structures and encouraging the expansion of voids. The key difference is the origin. In the Standard Model, dark energy is a mysterious new fundamental force that just happens to turn on and dominate at this specific era in cosmic history. In the Cyclic Model, this effect is a natural consequence of the universe's history. It's the lingering echo of a previous contraction and bounce, a cosmic momentum that was present from the very first moments and has been slowly fading ever since. The anomalies we see in the large-scale structure, those slightly too large voids and unexpected clustering patterns, could be the telltale signs of this inheritance. They aren't random statistical flukes. They are the specific fingerprints of a previous cosmic epoch, the architectural remnants of a universe that existed before our own, subtly guiding the construction of the one we call home. To grasp how something as seemingly insignificant as a quantum fluctuation could leave an imprint powerful enough to shape an entire universe, we need to dive into the bizarre and wonderful world of quantum physics. At the tiniest scales imaginable, the universe is never still. It is a seething, bubbling foam of pure potentiality. Empty space itself is not truly empty. It is a dynamic arena where pairs of particles and antiparticles spontaneously blink into and out of existence for unimaginably short moments. These are quantum fluctuations, temporary violations of the classical conservation of energy that are not just allowed but mandated by the Heisenberg uncertainty principle. They are the universe's fundamental background noise, and in our Standard Model of cosmology, it's believed that during a brief period of hyper-fast expansion called inflation, these tiny quantum ripples were stretched to astronomical sizes, becoming the gravitational seeds for all the galaxies and cosmic structures we see today. But what if our universe's story didn't start with its own inflation? What if it inherited its quantum seeds from a cosmos that came before? This is the profound shift in perspective offered by cyclic cosmology. In a model where the universe undergoes endless cycles of expansion, contraction, and rebirth, the process doesn't reset everything back to zero. The information, the quantum state of the previous cycle, isn't necessarily erased by a big crunch. Instead, it could be preserved, encoded in the fabric of spacetime itself as it undergoes a bounce. Think of it like a cosmic pendulum. When a pendulum swings, it doesn't just stop at the bottom of its arc. Its momentum carries it through to the other side. In a similar way, the quantum fluctuations that define the structure of a previous universe could carry their momentum and their pattern through the bounce, imprinting themselves onto the newborn universe that follows. This means the initial conditions for our own cosmic expansion weren't random, they were inherited. The quantum seeds for our galaxies were not purely our own, they might be the descendants of quantum seeds from an immeasurably ancient past. Now, let's connect this incredible idea directly to the mystery of dark energy. These inherited quantum fluctuations wouldn't just dictate where galaxies form, they could also influence the very dynamics of spacetime's expansion. The energy contained in these primordial ripples, a relic from a previous cosmic epoch, would be woven into the vacuum of space itself. As our universe expands, this residual vacuum energy would manifest as a persistent, repulsive pressure acting against the pull of gravity. From our perspective inside this cycle, this effect would be utterly indistinguishable from a cosmological constant or a dark energy field. We would measure an acceleration and, lacking any other explanation, attribute it to a new, mysterious substance. But in the cyclic view, it's not new at all. It's the ghost of a quantum past, a cosmic memory playing out on the grandest possible scale. This elegantly sidesteps the need to invent exotic new physics or particles. It simply suggests we are feeling the lingering effects of a quantum history that isn't solely our own. The power of this explanation lies in its naturalness. The standard model of cosmology has a glaring fine-tuning problem. The observed value of dark energy is inexplicably tiny compared to the value predicted by quantum field theory. It's like calculating the energy output of the sun and then measuring the power of a single candle flame and finding they are supposed to be the same. It makes no sense, but in a cyclic model, the value of this apparent dark energy isn't a fundamental constant, it's a dynamic artifact. It's the result of the specific quantum fluctuations that were carried over from the previous cycle, and it would naturally fade over time as the universe expands and the influence of that ancient memory dissipates. This framework doesn't just offer an alternative origin for dark energy, it provides a plausible reason for its curiously small value, transforming a baffling coincidence into a potentially understandable outcome of the cosmos's cyclical nature. This brings us to one of the most profound and mind-bending connections in all of physics, the intricate relationship between energy, information, and the very arrow of time itself. To understand how entropy could be the hidden key to the dark energy puzzle, we first need to grasp a concept that feels almost philosophical. Information is not abstract, it is physical. In our everyday lives, we think of information as bits and bytes on a hard drive or the words in a book. But in the universe's grand ledger, information is inextricably linked to the state of matter and energy. The arrangement of every atom, the spin of every electron, the precise gravitational curvature of spacetime around a galaxy, this is all information. And according to the fundamental laws of thermodynamics, particularly the second law, the total entropy, which is a measure of disorder or the loss of usable energy, always increases in an isolated system. It's the reason why an ice cube melts in a warm room but never spontaneously refreezes, why a shattered glass doesn't reassemble itself. This relentless rise in entropy defines the one-way direction of time's arrow, pushing the universe from a state of low entropy and high order after the Big Bang toward a future of maximum entropy, often called the heat death, where everything is evenly distributed, lukewarm, and devoid of any interesting structure or change. Now, this presents a monumental problem for the idea of a cyclic universe. If each cycle ends in a big crunch, a colossal compression of all matter and energy, you might think that would reset the entropy clock back to zero, creating a clean slate for the next cycle. But physics doesn't work that way. Gravitational collapse during a crunch doesn't decrease entropy, it dramatically increases it. A universe collapsing into a singularity would become a chaotic, high-entropy mess. So, if our universe is the latest in an endless series, it should have started with an enormous amount of inherited entropy, not the astonishingly low, finely tuned value we observe in the early cosmic microwave background. This is the infamous entropy problem, and for a long time it was considered a knockout blow against cyclic models. How could a universe be reborn with low entropy if its predecessor died in a state of maximum disorder? The revolutionary answer that has emerged turns this problem on its head. What if the information and the entropy isn't erased but is instead preserved and transformed across the cycle? Think of the universe not as a closed box but as a cosmic hard drive. During the contraction phase, as everything is crushed together toward the bounce, the information about the previous universe, the positions of its galaxies, the lives of its stars, isn't destroyed. It is compressed and encoded into the very fabric of spacetime itself, perhaps on its boundary or within the quantum degrees of freedom of the gravitational field. This is a concept physicists call holographic information storage. Then, during the subsequent Big Bang and expansion, that stored information isn't immediately readable as galaxies and stars. Instead, it manifests as a kind of latent energy inherent to the vacuum of space. It is the cosmic memory of that previous high entropy state, imprinted onto the new low entropy beginning. This is where the leap to dark energy happens. This preserved information, this accumulated entropy from eons of previous cycles, doesn't just sit there. It exerts a pressure. The universe in its new cycle is essentially wound up with this residual energy, and that energy acts as a repulsive force pushing space itself apart. From our vantage point inside the cycle, we measure this push, and seeing nothing else to account for it, we give it a name, dark energy. But in this view, it is not a mysterious substance. It is the thermodynamic echo of the universe's own history. The second law of thermodynamics, applied not to a single universe but to the entire multicycle cosmos, provides the engine. The drive toward increasing entropy doesn't reset. It continues across the bounds, and the manifestation of that drive in our young, expanding universe is the accelerating expansion we observe. The incredibly small but non-zero value of dark energy that so baffles physicists could simply be the precise amount of residual information that made it through the transition from the last cycle to ours, a value that is not fine-tuned by chance, but determined by the natural processes of information preservation across cosmic rebirth. This transforms dark energy from a foundational puzzle into a historical record, the lasting signature of everything that came before. Now we venture into one of the most mind-expanding domains of modern physics, a realm where the very nature of reality is far stranger and more magnificent than our three-dimensional senses can perceive. This is the world of brain cosmology, a framework born from the mathematics of string theory that suggests our entire universe might be just one thin slice of a much richer, higher-dimensional existence. In this view, the Big Bang wasn't a singular, inexplicable event from nothing, but the dramatic aftermath of a collision between cosmic membranes in a grand, higher-dimensional arena. And it is within this breathtaking paradigm that we find a compelling reason to reconsider dark energy not as a thing, but as a dynamic artifact of these deeper dimensional dynamics. To grasp this, we need to shift our perspective entirely. We are accustomed to living in a universe of three spatial dimensions: length, width, height plus time. But what if there are more? String theory, a leading candidate for a theory of quantum gravity, requires these extra dimensions for its mathematical consistency. It proposes that the fundamental constituents of reality are not point-like particles but incredibly tiny, vibrating strings. And within this framework, a fascinating idea emerged. Our entire three-dimensional universe could be a brain world, or simply a brain, a multidimensional membrane floating within a higher dimensional space called the bulk. Think of our universe not as an isolated bubble, but as a vast, impossibly thin slice of bread floating within a much larger loaf. Other brains, other universes, could be floating right alongside ours in this higher dimensional bulk, separated by distances in dimensions we cannot see or move through. This leads to a spectacular cyclic mechanism. The ekpyrotic model, a particular brain cosmology scenario, proposes that our universe's Big Bang was caused by a collision between our three-dimensional brain and another parallel brain moving through the bulk. This collision would have been cataclysmic, releasing an immense amount of energy that heated our brain to incredible temperatures, creating the hot, dense state we identify as the beginning of our cosmic cycle. But then the brains would bounce apart, driven by the forces between them, and our universe would begin to expand and cool on its own brain. Crucially, the model doesn't end there. The gravitational attraction between the brains would eventually pull them back together, leading to another collision, another bang, and another new cycle. This provides an elegant, mechanical explanation for a cyclic universe, all playing out in a hidden dimensional arena. So where does dark energy fit into this incredible picture? The key lies in the aftermath of the collision and the subsequent separation. When the brains collide and then spring apart, they don't just return to a perfectly neutral state. The interaction itself could leave our brain in a state of vibration or tension, like a drumhead that has been struck and is now humming with a specific resonant energy. This residual energy, inherent to the fabric of our brain itself as it floats in the bulk, would permeate all of space. Furthermore, the very act of the brains moving apart through the higher dimensional bulk could create a kind of pressure or potential energy field on our brain. From our limited three-dimensional perspective, trapped on our membrane, this pervasive energy would have a very specific effect. It would cause space itself to expand at an accelerating rate. We would measure this effect, calculate its strength, and with no knowledge of the higher dimensional drama, label it dark energy. But in the brain cosmology view, it is not a mysterious substance or a property of empty space. It is a direct byproduct, a side effect, of our brain's dynamic interaction with the larger multidimensional environment. This elegantly reframes the problem. The cosmological constant problem, the inexplicably small value of dark energy, might find a natural solution here. The value isn't arbitrary. It could be determined by the specific properties of the brain, such as its tension, or the precise distance and force between it and the other brain in the bulk. This framework doesn't just offer an alternative origin story. It integrates dark energy into a larger, more unified physical picture that includes gravity and the other forces, potentially offering a path to finally resolving one of cosmology's most stubborn mysteries. If the fine-tuning problems we've discussed so far feel abstract, consider this next one, a puzzle so profound that renowned physicist Wolfgang Pauli reportedly said it made him doubt we truly understand anything about the nature of reality. It's called the cosmological constant problem, and it represents perhaps the single largest discrepancy between theory and observation in the entire history of science. To grasp its magnitude, we need to go back to Einstein. When he first inserted the cosmological constant into his equations of general relativity, it was a sort of fudge factor, a term representing a constant energy density infused throughout the vacuum of space itself, which could act to either repel or attract. He later called it his greatest blunder, but the discovery of the accelerating universe brought it roaring back into fashion, as it perfectly describes a constant dark energy. The problem isn't the idea itself, but the number. When physicists try to calculate what the value of this vacuum energy should be using our well-tested theories of quantum mechanics, they arrive at an astronomical figure. They sum up all the fleeting quantum fluctuations, the particle-antiparticle pairs blinking in and out of existence in every cubic centimeter of empty space, and the energy density they predict is enormous. To put it in perspective, the calculated value is about 120 orders of magnitude larger than the value we actually observe. That's a 1 followed by 120 zeros. It's a number so ludicrously large that if the theoretical prediction were correct, the repulsive force of this vacuum energy would have been so powerful that it would have ripped apart every atom, star, and galaxy before any of them could even form. Our universe as we know it would be impossible. The fact that we exist to measure it, and that we measure a value so infinitesimally small in comparison, is the ultimate fine-tuning problem. It suggests that something is either deeply wrong with our theories, or that we are fundamentally misinterpreting what this energy is. This is where the cyclic universe model doesn't just offer an alternative. It provides a breathtakingly elegant escape hatch from this logical nightmare. In the standard model, the cosmological constant is just that, a constant. It's a fixed, fundamental property of the universe, a number that was set at the beginning of time and never changes. Its inexplicably small value is therefore a permanent, baffling feature of reality that we have to accept as a bizarre, anthropic coincidence. But in a cyclic cosmos, the force we call dark energy and attribute to a cosmological constant isn't fundamental at all. It's transient, it's dynamic, it's the fading echo of a previous cycle. Imagine you're trying to measure the average temperature of the Earth. If you take a measurement at the peak of a volcanic eruption, you'll get one number. If you take it during an ice age, you'll get another. But if you average your measurements over millions of years, you'll get a stable, moderate value that doesn't reflect the extreme highs and lows. A cyclic universe operates on a similar principle of averaging, but across cosmic timescales that are literally unimaginable. In each cycle, the apparent dark energy isn't a constant background value. It's a temporary phenomenon, a burst of repulsive energy that is generated by the mechanics of the bounce, the collision of brains, the rebound from a crunch, the transfer of information. This energy is potent at the start of a cycle, driving the initial rapid expansion, but it naturally dissipates and decays as the cycle progresses. Now, if you could somehow average the strength of this repulsive force not over one cycle, but over trillions upon trillions of cycles, what would you get? You would get a very, very small number, a number that is effectively zero for most of the cycle's duration, punctuated by brief spikes. From our limited perspective, trapped inside a single cycle, we are measuring the universe during one of those spikes. We see a small but non-zero value for dark energy and mistake it for a constant. The cyclic framework completely reframes the problem. The value isn't fine-tuned, it's averaged. The incredibly small number we measure isn't a mysterious fundamental constant. It's simply the current value of a dynamic, decaying artifact from the last cosmic rebirth. This transforms the greatest embarrassment in theoretical physics into a natural, expected outcome of a universe with an infinite and cyclical history. But what if this foundational assumption is wrong? What if the very force we've been trying to measure isn't a steady, unchanging constant, but something far more dynamic and alive? This brings us to a crucial and growing body of evidence that is quietly shaking the pillars of modern cosmology, the possibility that dark energy itself is changing over time. The standard model, Lambda CDM, is built on the idea of a cosmological constant, a perfectly uniform energy that has the same repulsive strength today as it did billions of years ago and will have billions of years from now. It's a simple, elegant idea, but nature often favors complexity over simplicity. Recent observations, particularly from the Dark Energy Survey and other ambitious sky mapping projects, have begun to hint at something fascinating. The data doesn't conclusively prove it yet, but it strongly suggests that the equation of state for dark energy, the parameter that describes the relationship between its pressure and density, might not be fixed at the magical number of -1, which signifies a constant. Instead, it seems to wiggle. It might have been slightly stronger in the past or could be weakening now. This isn't just a minor statistical fluctuation, it's a potential revolution. If dark energy's strength is time-varying, it means our universe's acceleration isn't on a fixed, predetermined course. It's evolving, and that single idea dismantles the entire premise of a cosmological constant, forcing us to consider a much more fluid and historical explanation for what we're seeing. This is precisely where the cyclic universe model doesn't just step in to help, it confidently predicts such behavior. Remember, in a cyclic cosmos, the apparent dark energy isn't a fundamental feature of the vacuum. It's a residual effect, a kind of cosmic exhaust left over from the colossal event that birthed our cycle. Think of it like the warmth from a stone that's been sitting in the sun all day. If you bring that stone inside at night, it doesn't stay hot forever. It radiates its stored heat, gradually cooling down until it reaches the temperature of the room around it. In exactly the same way, the repulsive energy inherited from the previous cycle's bounce or brane collision wouldn't be permanent. It would be a transient phenomenon. It would be strongest immediately after the Big Bang, providing that initial kick to expansion, and then it would gradually dissipate over the eons as the universe expands and dilutes this residual influence. From our perspective, living several billion years into the cycle, we would be measuring this energy in its fading phase. We wouldn't see a steady push, we would see a force that is very, very slowly losing its strength. This dynamic, time-dependent behavior is not an add-on or a patch to the cyclic model. It is an intrinsic, unavoidable feature of its core mechanics. The model was built on the idea of a fading echo, so the discovery of a varying dark energy would be a powerful validation of its central premise. The implications of this are profound for resolving the other tensions we've discussed. The Hubble tension, that frustrating discrepancy between early and late measurements of the expansion rate, could be elegantly resolved if the repulsive force was stronger in the early universe than our constant models assume. The Planck satellite measuring conditions from the early cosmos would have felt the effect of a more potent dark energy, leading to one prediction for today's expansion rate. Our local measurements, which probe the more recent, weaker phase of dark energy, would give a different result. The tension isn't an error. It's a clue that we are measuring the force at two different points in its life cycle. Furthermore, a dynamic dark energy would naturally lead to different patterns in the large-scale structure of the universe than a constant one. The way galaxies cluster and voids form would be subtly influenced by a force that is slowly fading, potentially explaining those small but persistent anomalies that standard simulations struggle to replicate. This time-varying nature transforms dark energy from a mysterious, static placeholder into a dynamic character in the cosmic story, one with a history and a future that is intimately tied to the cyclical rebirth of the universe itself. This brings us to one of the most profound and seemingly intractable puzzles in all of theoretical physics, the black hole information paradox. At its heart, this is a conflict between the two great pillars of modern physics, the rock-solid, deterministic laws of quantum mechanics and the curved, relativistic reality of Einstein's general relativity. According to quantum mechanics, information is sacred. It can never be truly created or destroyed. It might be scrambled like an egg, but it should always be possible, in principle, to unscramble it and recover the original data. This is a fundamental tenet of our understanding of the universe, but then we have black holes predicted by general relativity. When a star collapses into a black hole, it forms an event horizon, a point of no return, and a singularity at its core, a point where the laws of physics as we know them simply break down. Stephen Hawking made a startling discovery. Black holes aren't completely black. They slowly radiate away their mass through a subtle quantum process, now known as Hawking radiation. The problem is, this radiation appears to be completely random, carrying no information about the material that originally fell in. If a black hole evaporates completely over eons, disappearing in a final puff of Hawking radiation, what happened to all the information about the stars, planets, or astronauts that fell into it? Was it irretrievably lost at the singularity? This violation of quantum law is the information paradox, and it suggests that our current understanding of gravity or quantum physics is deeply incomplete, missing a crucial piece that would allow these two worlds to reconcile. For decades, physicists have proposed various solutions. Some suggest the information is encoded on the event horizon itself. a holographic surface that preserves the data of everything that falls in. Others propose that information might slowly leak out in the Hawking radiation in incredibly subtle ways. But there is another, far more grand solution. The information isn't lost at all because the black hole isn't a final destination. It's a transfer point. This is where the concept of a cyclic universe offers a breathtakingly elegant resolution. In a cosmos that undergoes endless cycles of expansion and contraction, the ultimate fate of a black hole might not be evaporation into nothingness. In the far, far future of our universe, as expansion potentially gives way to a gradual contraction, everything, including every last black hole, would eventually be drawn together. In some cyclic models, this doesn't lead to a destructive singularity that erases everything, but to a cosmic bounce. A black hole singularity might not be a wall but a tunnel, a gateway through which information is not destroyed, but rather compressed and preserved, ready to be imprinted onto the fabric of the next universe during the rebound. The information isn't lost, it's just on the other side of a cosmological reset, waiting for the next cycle to begin. Now, let's connect this monumental idea to the mystery of dark energy. If information is preserved across cycles and is somehow imprinted onto the new, expanding universe, it must manifest itself in some physical way. Information is not abstract. In physics, it is physical. It has energy and structure. The act of preserving this colossal amount of data, the quantum states of every particle that ever fell into every black hole across a previous cosmic epoch, would require an enormous amount of energy. This energy wouldn't just sit there passively. It would be woven into the vacuum of space-time itself as a kind of latent potential. As the new universe expands, this preserved information energy would exert a pressure, a force acting against the gravitational pull of ordinary matter. From our perspective inside the cycle, this would look exactly like a repulsive force driving the acceleration of the universe. We would measure its effect and call it dark energy, completely unaware that what we are actually detecting is the physical manifestation of cosmic memory, the preserved information from black holes and all other structures from a universe that existed before our own. This framework provides a stunningly unified view of reality. The black hole information paradox, one of the deepest problems in quantum gravity, and the mystery of dark energy, the dominant component of the universe, might not be separate puzzles at all. They could be two sides of the same coin, both solved by the same underlying principle, the cyclical preservation of information. Dark energy ceases to be an exotic, unexplained substance, and instead becomes a thermodynamic consequence of the universe safeguarding its own history. It is the energy cost of ensuring that not a single bit of information is ever truly lost, a cosmic safeguard that manifests as the accelerating expansion we measure today. This idea ties the fate of the very largest structures in the cosmos, black holes, to the behavior of the universe on its grandest scales, suggesting that the key to understanding dark energy has been hidden in the paradox of information loss all along. But to truly appreciate how these cosmic ripples could rewrite the story of dark energy, we first need to understand what the gravitational wave background is and why it's considered the next great frontier in astronomy. Gravitational waves are not like light or radio waves. They are literal ripples in the fabric of spacetime itself, first predicted by Einstein over a century ago and directly detected for the first time only in 2015. These waves are created by the most violent and energetic events in the universe, the collisions of black holes and neutron stars, the explosions of supernova, and even the primordial tremors from the birth of the cosmos. Each event sends out a faint shudder through the very structure of reality, and these signals travel across the universe, stretching and squeezing everything in their path by almost unimaginably tiny amounts. Now, while we can detect the loud, individual crashes from recent cosmic collisions, there's a far more subtle and pervasive signal that scientists are now hunting: the gravitational wave background. Imagine standing on a shore and listening to the occasional large, crashing wave. That's like our current detection of individual black hole mergers. But now, try to listen for the combined, steady hum of every single wave from every ocean on Earth all at once, a constant, low-frequency rumble that underlies everything. That is the gravitational wave background. It's the integrated hum of every gravitational wave event that has ever occurred throughout the entire history of the universe, all overlapping to create a steady, universe-filling symphony of spacetime vibrations. Detecting this background is the ultimate goal of projects like pulsar timing arrays, which use the incredibly regular flashes of light from distant neutron stars as a galactic-scale ruler. As a gravitational wave passes between us and one of these pulsars, it minutely alters the timing of its pulses, and by monitoring networks of these pulsars for decades, we can eventually piece together the pattern of this underlying hum. The standard cosmological model, with its constant dark energy, makes very specific predictions about what this gravitational wave background should sound like. It predicts a certain spectrum of frequencies and a particular amplitude or loudness, based on the types of events we expect to have occurred and how the expansion history of the universe has stretched those waves over time. But what if, when we finally tune our instruments to hear this cosmic symphony with perfect clarity, the music doesn't match the score? This is the tantalizing possibility that cyclic cosmology presents. In a universe that has undergone countless cycles of expansion and contraction, the gravitational wave background would be immeasurably richer and more complex. The most dramatic source of waves wouldn't just be the events within our own cycle. It would be the cataclysmic finale of the previous one. The final moments of a universe contracting toward a big crunch would be a gravitational wave apocalypse. As galaxies, clusters, and eventually entire superclusters are pulled together by the overwhelming force of contraction, they would collide in a frenzy of mergers, generating a deafening roar of gravitational waves. Furthermore, the process of the bounce itself, whether it's a quantum rebound or a brain collision, would unleash a shockwave of primordial gravitational radiation of an intensity we can scarcely imagine. This crescendo of waves from the end of time would then be imprinted onto the newborn universe, its frequencies stretched and reddened by the subsequent expansion of our own cycle, but its fundamental character forever bearing the signature of that violent transition. From our perspective inside this cycle, this inherited rumble would be superimposed on the gravitational waves generated by our own universe's events. When we listen to the background hum, we wouldn't just be hearing the collisions from our history, we would be hearing the ghostly echo of a cosmic death from an epoch long past. The spectrum of this background would likely show anomalies, an unexpected amount of power at certain low frequencies, or a statistical pattern that simply doesn't align with the predictions of a universe that began only once with a big bang. We might misinterpret this extra oomph in the gravitational wave background, attributing it to a stronger influence from dark energy on the wave production in our own cycle, when in fact it is not a product of dark energy at all. It is the direct evidence of the cycle itself, a fossil record of gravitational waves preserved from a previous cosmic era. The detection of such an anomaly would be a monumental discovery, providing the first direct, tangible evidence that our universe is not a one-time event but part of an infinite, cyclical process, and in doing so, it would powerfully reframe the acceleration we see not as the work of a mysterious dark energy, but as the continuing momentum from a rebirth we are only now learning to hear. While the idea of a universe accelerating apart due to dark energy is strange enough, some of its more extreme theoretical versions paint a picture of a future so violently catastrophic that it borders on the apocalyptic. This is the realm of phantom energy, a hypothetical form of dark energy that is even more repulsive than the standard cosmological constant. In this unsettling scenario, the strength of dark energy isn't constant, it actually increases over time. The equation of state, the parameter that describes its pressure-to-density ratio, would be less than -1, pushing it into this phantom territory. The consequences of such a force are not just dramatic, they are utterly final. As phantom energy grows in strength, it would eventually overcome every single force that holds the universe together. First, the gravitational bonds of galaxy clusters would be severed, sending galaxies flying apart on lonely trajectories into the expanding darkness. Then, the very galaxies themselves would be torn asunder, stars ripped from their orbital paths. Closer to the end, planetary systems would be unbound. And finally, in the last terrifying moments, the phantom energy would become so powerful that it would overwhelm the nuclear forces holding atoms together. Molecules, then atoms, and ultimately the very fabric of subatomic particles would be violently ripped apart in a final, instantaneous event known as the Big Rip. It is the ultimate cosmic doomsday, a finale of absolute nothingness where not even the building blocks of reality remain. This grim prognosis, however, rests entirely on the assumption that dark energy is a fundamental, standalone component of the universe that will continue to behave according to this specific, terrifying model. It assumes a linear timeline with a definitive and absolute end. But the cyclic universe model completely reframes this narrative, transforming a terrifying conclusion into a transitional phase. In a cyclic cosmos, the apparent acceleration we measure today, even if it has phantom-like qualities, is not a one-way ticket to oblivion. It is simply one phase in a much grander, repeating cycle. The repulsive force we call dark energy is understood not as a fundamental entity, but as a temporary residue, the leftover momentum or energy from the rebound that initiated our current cycle. Just like any echo or wave, it has a peak intensity and then it naturally fades. In this view, a phantom-like effect wouldn't be a sign of permanent doom, but merely an indication that the repulsive phase of our current cycle is particularly strong. It's a powerful exhale, but not the universe's final breath. The beautiful mechanics of a cyclic model inherently prevent a true Big Rip from ever occurring. The expansion phase, no matter how accelerated, is not eternal. Eventually, the repulsive energy inherited from the bounce will dissipate, its influence diluted by the relentless expansion it helped to create. As it fades, gravity, the persistent attractive force of all the matter and dark matter in the universe, will begin to reassert its dominance. The acceleration will slow, then halt, and a gradual contraction will begin. This is the critical turning point that a linear model lacks. The universe avoids the sterile fate of a heat death or the violent demise of a Big Rip because its very structure is programmed for renewal. The contraction phase gathers everything together, not to be destroyed in a rip, but to be reconfigured and reborn in the next bounce. What appears from our limited viewpoint to be a phantom energy driving us toward destruction is actually just the natural and temporary recoil from a previous cosmic contraction, setting the stage for the next act in an infinite drama. This perspective doesn't just solve a theoretical problem. It fundamentally alters the emotional and philosophical weight of dark energy, recasting it from an agent of ultimate doom into a necessary and passing phase in the universe's eternal rhythm of renewal. To truly grasp why the quantum vacuum is such a compelling candidate for dark energy, we need to peer into the bizarre and counterintuitive world that exists at the very smallest scales. We often think of empty space as just that empty, a perfect, featureless void, but according to our most fundamental laws of quantum physics, this couldn't be further from the truth. What we perceive as a vacuum is actually a seething, bubbling cauldron of pure potentiality. At scales trillions of times smaller than an atom, the universe operates under the rules of the Heisenberg uncertainty principle, which essentially states that you can never have a perfectly quiet, perfectly still system. There is always a fundamental jitter, a background hum of existence. Because of this, pairs of virtual particles and antiparticles spontaneously blink into and out of existence for unimaginably short moments, borrowing energy from the vacuum itself before annihilating and paying it back. This isn't just theoretical. We see the effects of these quantum fluctuations in lab experiments, like the Casimir effect, where two metal plates placed incredibly close together in a vacuum are gently pushed together by the pressure of these virtual particles popping into existence outside the plates. This frenetic activity means that every single cubic centimeter of what we call empty space is actually brimming with a colossal amount of energy. This is the quantum vacuum energy, or zero-point energy, and when physicists try to calculate its theoretical density, they arrive at a number so enormous it defies comprehension. It should be the most powerful force in the universe by an almost laughable margin, making the energy output of all the stars in all the galaxies look utterly insignificant by comparison. This is the heart of the cosmological constant problem we touched on earlier. The calculated vacuum energy density is about 120 orders of magnitude larger than the tiny, gentle repulsive force we actually observe and call dark energy. It's the single worst prediction in the entire history of physics. So if this vacuum energy is real and so unimaginably powerful, why isn't it tearing the universe apart? The standard approach has been to assume that for some unknown reason, the positive energy of these particle fluctuations and the negative energy of the gravitational field between them somehow cancel each other out almost perfectly, leaving behind only the tiniest, most minuscule residue, and that residue is what we call dark energy. This requires a level of fine-tuning so precise it seems absurd, like balancing a pencil on its tip for billions of years in a hurricane. It feels less like a scientific explanation and more like a metaphysical miracle. This profound failure of the standard model is what forces us to look for a better answer, and the cyclic universe provides a stunningly elegant way out of this logical trap. In a cyclic cosmos, the vacuum energy isn't a static, eternal background value. It's dynamic and historical. Imagine each universe in the cycle is like a wave on the ocean. The wave rises, peaks, and then falls, dissipating its energy. The quantum vacuum isn't immune to this process. During the contraction phase of a cycle, as everything is crushed together toward the bounce, the very structure of spacetime is fundamentally reshaped. The modes of vibration that allow for these quantum fluctuations are altered, and the energy of the vacuum itself can be effectively reset or scrambled. Then, during the bounce and the subsequent expansion of the new cycle, the vacuum energy doesn't just snap back to its full, theoretical value. It begins at a much lower level and gradually builds up as the universe expands and new quantum states become available. But here's the crucial insight from the cyclic model. It doesn't start from zero. Each new cycle inherits a residual vacuum energy from the universe that came before. It's not a full reset, it's a renewal that carries forward a memory of the past. This changes everything. the apparent dark energy we measure in our universe isn't the inexplicably tiny leftover from a near-perfect cancellation in our one and only universe. Instead, it is the accumulated residue of vacuum energy from countless previous cycles. Each cycle contributes a small amount of this residual vacuum energy, and over eons of cosmic repetition, these tiny contributions sum up to the specific value we observe today. It's not a finely tuned constant, it's a historical artifact, a running total. Think of it like a savings account. You don't deposit the entire massive sum all at once. You make small, regular deposits over a long period of time, and eventually it adds up to a significant amount. In this view, the vacuum energy we call dark energy is the cosmic savings account, built up over infinite cycles. This framework completely bypasses the nightmarish fine-tuning problem. The value isn't a miracle, it's simply the current balance in an account that has been active for eternity. It reframes dark energy from a mysterious new substance to the natural, accumulated effect of the quantum vacuum's own ancient and cyclical history. For decades, dark matter and dark energy have been treated as the universe's most famous strangers, two separate, enigmatic entities that dominate the cosmos yet seem to operate in complete isolation from one another. Dark matter, the invisible scaffolding that holds galaxies together with its gravitational pull, accounts for about 27% of the universe. Dark energy, the mysterious repulsive force accelerating the expansion, makes up nearly 70%. In the standard model, they are like two actors on a dark stage, one building structures while the other pushes them apart, never interacting, never communicating, governed by entirely different rules. But what if this clean separation is an illusion? What if these two great unknowns are not strangers at all, but deeply connected players in a much larger, cyclical drama? This tantalizing possibility suggests that dark energy might not be a fundamental force, but rather a secondary effect, a kind of cosmic exhaust produced by the slow evolution of dark matter itself over unimaginable cycles of time. To understand how this could work, we first need to reconsider the nature of dark matter. We know it exists because of its overwhelming gravitational influence. Without it, galaxies would fly apart and the cosmic web would never have formed. But we have no idea what it's actually made of. The leading candidates are theoretical particles like WIMP, or weakly interacting massive particles, which are thought to be stable and virtually unchanging over the lifetime of our universe. But this assumption of stability is just that, an assumption. In the vast expanse of a cyclic cosmos, where time is measured in trillions upon trillions of years, perhaps dark matter isn't so stable after all. Some compelling theoretical models propose that dark matter particles could very slowly decay or transform into something else. This process wouldn't be fast or dramatic. It would be a gradual, cosmological scale metamorphosis, like a mountain slowly eroding into sand over eons. And just as erosion releases energy and matter into the environment, the decay or transition of dark matter would release energy into the fabric of space-time. Now imagine this process not just in our one universe, but across an endless sequence of cosmic cycles. In each cycle, a portion of the dark matter left over from the previous epoch undergoes this slow transformation. The energy released from this decay wouldn't vanish, it would permeate the vacuum of space, and because this energy is being added to the universe continuously and uniformly, it would manifest as a persistent, gentle pressure pushing space itself apart. From our perspective, observing this effect over just a tiny fraction of a single cycle, this would look exactly like a constant, repulsive dark energy. We would detect the acceleration and, seeing no other cause, attribute it to a new fundamental component. But in reality, What we're calling dark energy could simply be the faint glow from the slow-burning candle of dark matter decay, a secondary phenomenon arising from the life cycle of the universe's dominant invisible substance. This idea of interconnection is powerfully supported by certain anomalies in our observations. For instance, the observed relationship between the amount of dark matter in a galaxy and its distribution of ordinary matter isn't always perfectly aligned with computer simulations. There are hints that dark matter might be interacting with itself in ways we don't fully understand, or that its influence on galaxy formation is more complex than a simple gravitational pull. In a cyclic model, these subtle inconsistencies could be the fingerprints of this deep connection. The residual energy from dark matter decay in previous cycles could have subtly altered the initial conditions for structure formation in our own universe, leading to the patterns we see today. This framework doesn't just offer an alternative origin for dark energy. It weaves the two great mysteries of modern cosmology into a single, elegant narrative, suggesting that to solve one, we must finally understand the other. This idea of a deep, historical connection between the universe's components leads us to one of the most elegant symmetries in all of cosmology: the potential link between the very first moments of our universe and its ultimate fate. To appreciate this, we need to rewind the cosmic clock back to a fraction of a second after the Big Bang, to an era so early and so extreme that our current physics can only speculate about what happened. This is the domain of cosmic inflation, a theory proposed to solve several major puzzles about our universe's initial conditions. The theory posits that the newborn cosmos underwent a period of exponentially rapid expansion, inflating from a subatomic speck to something much, much larger in an almost unimaginably short burst. This violent stretching would have smoothed out the universe, making it remarkably flat and uniform on large scales, while also magnifying tiny quantum fluctuations into the density variations that later seeded all the galaxies and cosmic structures we see today. Inflation is a powerful idea, and it fits a lot of the data we have from the cosmic microwave background beautifully, but it has always had a strange, almost philosophical caveat. It's a one-time event, a singular, unexplained trigger that started the universe as we know it and then shut off, never to happen again. It explains the beginning, but it stands alone, disconnected from the later story of dark energy. But what if inflation isn't a one-off event? What if it's not the beginning of the story, but a recurring chapter? This is where the cyclic universe model weaves these two colossal ideas, inflation and dark energy, into a single, continuous narrative. In many cyclic theories, the process that initiates a new cycle, whether it's a brain collision or a quantum bounce from a previous contraction, doesn't just create a hot, dense state. It naturally produces a period of incredibly rapid expansion. This rebound inflation would look, for all intents and purposes, exactly like the inflationary period we postulate for our own Big Bang. It would smooth out the universe, set up the initial density fluctuations, and then gracefully hand over the reins to the more sedate expansion governed by the radiation and matter that fill the new universe. In this view, inflation isn't a unique mystery. It's a standard part of the cosmic cycle's reboot sequence, happening at the start of every new universe. Now, here is the critical connection to dark energy. This period of rebound inflation, like any powerful physical process, wouldn't just cleanly switch off without a trace. It would leave behind residues, aftereffects, and imprints. Think of it like a powerful engine starting up. When you turn the key, the engine roars to life with a burst of energy, and then it settles into a steady hum. But even after it settles, the engine is still warm, vibrating slightly, and filled with the latent energy of that initial ignition. In a similar way, the inflationary burst at the start of a cycle could leave a persistent energy infused within the vacuum of spacetime itself. This residual energy from the inflationary process would be a form of vacuum energy, and as the universe expands in its post-inflation phase, this energy would begin to dominate, acting as a constant, repulsive force pushing space apart. From our vantage point billions of years later, we would detect this acceleration and call it dark energy, completely unaware that we are actually measuring the fading echo of our own universe's inflationary birth cries. This framework is profoundly powerful because it unifies the two great acceleration epochs of the cosmos, the very early inflation and the late-time dark energy acceleration, under one single, elegant mechanism. They are not two separate, unrelated puzzles. They are simply the same phenomenon witnessed at two different stages of the cosmic cycle: the intense, brief burst at the very beginning and its long, slow tail at the end. This resolves a major conceptual headache in cosmology. We no longer need to invent one exotic mechanism to explain the universe's initial rapid expansion, and a completely different, unrelated exotic substance to explain its current acceleration. Instead, we have a single, cyclical process that accounts for both, weaving the entire history of the universe into a coherent, continuous story where the end of one phase naturally seeds the beginning of the next. The force we call dark energy becomes the final, gentle expression of the very same power that forged our universe in the first place, a cosmic signature that links our present directly back to the moment of our own cosmic reboot. One of the most powerful tools in a cosmologist's arsenal isn't a telescope, but a supercomputer. These machines allow us to build intricate virtual universes, governed by the laws of physics as we understand them, to see how they evolve over billions of simulated years. For decades, the gold standard has been to program these simulations with the Lambda CDM recipe, a mix of ordinary matter, cold dark matter, and a fixed dose of dark energy represented by Einstein's cosmological constant. When we run these simulations, they produce a universe that looks remarkably like our own, complete with a cosmic web of galaxies and clusters, which is a huge part of why the standard model has been so successful. But this success comes with a significant caveat. It assumes the answer from the very beginning. The simulations are built to include dark energy because we observe acceleration. They then show that with dark energy, you get a universe like ours. It's a powerful consistency check, but it doesn't prove that dark energy is a fundamental reality. It only proves that our models can be tuned to match the data if we include it. This is a subtle but crucial distinction, and it's what makes the work on simulating cyclic models so revolutionary. Instead of starting with a pre-programmed dark energy constant, a number of research teams have taken a radically different approach. They build their virtual universes from the ground up based on the mathematical principles of cyclic cosmologies, whether it's the ekpyrotic model of colliding branes or a quantum bounce from a previous contraction. These models have their own set of initial conditions and governing equations, and notably, they do not include a cosmological constant or any form of inherent dark energy. The repulsive force isn't an input, it's a potential output. When scientists run these simulations, they watch as the virtual universe expands from its bounds. And time and again, they observe something fascinating. A phase of accelerated expansion naturally emerges from the dynamics of the cycle itself. It's not something that was added, it's something that develops organically from the physics of the model. The residual energy from the bounce, the inherited quantum fluctuations, or the latent vacuum energy from the previous cycle, whatever the specific mechanism, manifests as a pressure that drives the universe apart in a way that is, for all observational purposes, indistinguishable from dark energy. The implications of this are staggering. It suggests that the phenomenon we've labeled dark energy could be a computational artifact, not in the sense that it's not real, but in the sense that it's an emergent property of a more complex underlying reality, much like the temperature of a gas emerges from the chaotic motion of countless individual molecules. When we use a simpler one-cycle model that lacks this historical depth, we have to manually insert a fudge factor, the cosmological constant, to get the right answer. The cyclic simulations show that if you use a more complete model that accounts for the universe's potential cyclical history, that fudge factor becomes unnecessary. The acceleration writes itself into the code. This doesn't just offer an alternative explanation, it challenges the very methodology of modern cosmology. It raises the possibility that we have been mistaking a consequence for a cause, that dark energy is not the driver of acceleration but merely our name for the effect, a simplified label we've applied to a symptom of a much deeper and more ancient cosmic process. The success of these simulations doesn't yet prove the cyclic model is correct, but it powerfully demonstrates that a universe without fundamental dark energy can look exactly like ours, forcing us to question whether our most cherished assumptions have been blinding us to a more elegant truth. This brings us to a concept that bridges the gap between the deeply physical and the profoundly philosophical, the anthropic principle. At its core, this principle is a simple statement of observational selection bias. The universe we are capable of observing must be one that has the necessary conditions for our existence as observers. We shouldn't be surprised to find ourselves in a universe with constants and laws that allow for galaxies, stars, planets, and ultimately, life. If any of these fundamental numbers were even slightly different, if the strength of gravity were altered by a fraction of a percent, or the nuclear forces were a tiny bit weaker, the cosmos would be a sterile void, incapable of producing the complex structures that lead to us. In the Standard Model, dark energy is the ultimate example of this mind-boggling fine-tuning. The value we measure is absurdly small, yet if it were even slightly larger, the universe would have blown itself apart before the first stars could form. If it was zero or negative, the universe would have collapsed back in on itself long ago. Our existence seems to hinge on a cosmic lottery win of unimaginable odds, a stroke of incredible luck that leaves many scientists deeply uncomfortable, as it feels less like a scientific explanation and more like a metaphysical shrug. This is where the concept of a cyclic universe doesn't just offer an alternative mechanism, it provides a powerful and elegant philosophical resolution to the fine-tuning problem. In a single, linear universe that begins only once, the specific value of dark energy is a fixed, immutable initial condition. It's a brute fact of existence that we simply have to accept as a given, a lucky number drawn from a near-infinite set of possibilities. But in a cyclic cosmos, the rules of the game are completely different. Instead of a single roll of the dice, you have an infinite number of rolls across an endless series of universes. Each cycle or each bubble universe in a larger multiverse can have slightly different physical parameters. Most of these universes would be stillborn, collapsing instantly, flying apart too quickly, or simply lacking the right conditions for any interesting complexity to ever arise. But every so often, through the sheer statistics of infinite tries, a universe will emerge with parameters that allow it to be long-lived, expansive, and fruitful. In this grand Darwinian-like selection process on a cosmological scale, a universe that possesses a small, non-zero value for what we call dark energy isn't a miraculous anomaly, it's a predictable outcome. A modest amount of repulsive energy allows a universe to avoid a premature Big Crunch and expand long enough for stars to forge heavy elements and planets to form. But crucially, if that energy is too strong, if it's a phantom energy that leads to a big rip, it also terminates the cycle, preventing that universe from ever giving birth to a successor. Therefore, the cycles that persist, the ones that can successfully lead to a rebound and a new universe, are naturally selected to be those with a stable, long-lasting expansion phase. Universes with a destructive amount of dark energy are evolutionary dead ends. The value we measure isn't a finely tuned constant set at the beginning of time. It's the result of a cosmological selection bias. We don't live in a universe with a special value for dark energy. We live in a type of universe that has persisted long enough to produce us and is capable of continuing the cycle. The apparent fine-tuning is an illusion created by our limited perspective. We are not seeing a lucky winner of a 1 in a gazillion lottery. We are simply living in one of the few stable, self-perpetuating cycles that form a permanent branch on the infinite tree of cosmic possibility. This reframes dark energy from a mysterious, finely tuned substance to a natural, emergent property of a universe that has been selected for its longevity and stability. This profound connection between time, disorder, and the very direction of causality itself brings us to a concept that feels almost philosophical, yet is grounded in the most fundamental law of physics, the thermodynamic arrow of time. We all intuitively feel time moving forward. We remember the past, we anticipate the future, and we watch as ice cubes melt in a drink, smoke disperses in a room, and buildings eventually crumble, process that never, ever spontaneously reverse themselves. This one-way direction of time's flow isn't just a psychological phenomenon. It's a physical one governed by the second law of thermodynamics, which states that the total entropy or disorder of an isolated system always increases. The universe as a whole is moving from a state of low entropy and high order, like the incredibly smooth, hot, dense soup of the early cosmos, toward a state of maximum entropy, a cold, dark, evenly distributed equilibrium often called the heat death, where no interesting work can be done and no new structures can form. This relentless rise in entropy is what gives time its arrow, its undeniable forward direction. Now, this presents a monumental challenge for any cyclic model of the universe. If our universe is the latest in an endless series, what happens to all that entropy at the end of each cycle? When everything collapses in a big crunch, you might hope that all that disorder gets reset, wiped clean for a fresh start. But physics doesn't work that way. Gravitational collapse is a fantastically efficient entropy-producing machine. A universe ending in a crunch would be a chaotic, high-entropy mess. So how could our universe have begun with the astonishingly low entropy we see in the early cosmic microwave background, if it was born from the high-entropy ashes of a predecessor? This entropy problem has long been considered a knockout argument against eternal cycles. The solution, however, might be one of the most elegant ideas in all of cosmology. Perhaps the entropy isn't reset, but is instead preserved, transferred, and transformed across the bounds, and it is this very process that manifests as the force we call dark energy. Think of the universe not as a closed box, but as a cosmic hard drive. During the contraction phase of a cycle, as galaxies, stars, and eventually spacetime itself are compressed toward the ultimate bounds, the information, the specific arrangement of every particle, the total entropy of the entire cosmos isn't erased. According to principles from quantum gravity and holography, this information could be encoded onto the boundary of the universe or within the quantum structure of the gravitational field itself. It's compressed and stored like a massive zip file at the moment of the bounce. Then, as the new universe explodes into existence and begins to expand, that stored information isn't immediately readable as galaxies and stars. Instead, it unravels and manifests as a latent energy permeating the vacuum of space. This energy is the physical embodiment of the previous universe's history, its entropy, its memory. This is where the leap to dark energy becomes clear. This preserved information energy, this imprint of a previous high entropy state onto a new, low entropy beginning, doesn't just sit there passively. It exerts a pressure. The universe is, in a sense, wound up with this residual energy from its past, and that energy acts as a repulsive force, pushing the fabric of space-time apart. From our perspective inside the cycle, we measure this persistent push against gravity, and finding no other source, we label it dark energy. But in this breathtaking view, it is not a mysterious substance. It is the thermodynamic echo of the universe's own history. The drive toward increasing entropy doesn't reset at the bounce. It continues, and its manifestation in our young, expanding universe is the accelerating expansion we observe. The incredibly small but non-zero value of dark energy could simply be the precise amount of residual information energy that made it through the transition, a value determined not by chance but by the natural processes of cosmic information preservation. This transforms dark energy from a foundational puzzle into a historical record, the lasting signature of everything that came before, tying the force that shapes our cosmic future directly to the deep, thermodynamic past of a cycle we can no longer see. For decades, our cosmic story had a clear and comforting timeline. After the Big Bang, the universe expanded and cooled, allowing gravity to slowly, patiently pull together the first wispy clouds of gas into the earliest, simplest protogalaxies. These infant structures would then take hundreds of millions, even billions, of years to mature into the grand, well-ordered spiral and elliptical galaxies we see in our local universe. This gradual evolution was a cornerstone of our models, a predictable progression neatly explained by the interplay of dark matter's gravitational pull and dark energy's later push. Then the James Webb Space Telescope opened its golden eye and turned that entire story on its head, revealing a universe's infancy that looks nothing like what we thought we knew. The data from Webb is nothing short of revolutionary and for cosmologists more than a little bewildering. Instead of finding a primordial cosmos filled with small, chaotic, and fragile baby galaxies, Webb is seeing giants in the nursery. It has discovered a surprising number of massive, incredibly bright, and fully formed galaxies at distances and therefore at times so early that, according to our standard models, they simply shouldn't exist. We're seeing vast, mature disks and massive clusters of stars that appear to have assembled in a fraction of the time our theories said was possible. It's like walking into a kindergarten classroom and finding a group of teenagers. The timeline is fundamentally, dramatically broken. These galaxies are too big, too soon. Their sheer presence suggests that the early universe was able to build complex structures at a ferocious, almost violent pace, a rate of formation that the standard Lambda CDM model, with its prescribed slow dance of dark matter and dark energy, struggles desperately to explain. This isn't just a minor anomaly, it's a direct challenge to our understanding of how cosmic structure itself is built. This is precisely where the concept of a cyclic universe moves from a fascinating alternative to a potentially crucial solution. In the standard one-cycle model, the universe starts with a clean slate. The initial conditions are set by inflation, and everything that follows the formation of the first stars, the assembly of the first galaxies, has to happen from scratch within the 13.8 billion-year timeline we've measured. But in a cyclic model, the slate is not clean. It is preloaded with a cosmic memory. The new universe is born not from nothing, but from the ashes of a previous one, and it inherits the residual energies, the gravitational echoes, and the quantum imprints of that ancient past. This means that from the very first moment of our Big Bang, the universe wasn't starting from zero. It was already pregnant with structure, already imbued with a latent potential for complexity. Think of it like trying to grow a forest. In the standard model, you start with barren, empty soil. You have to wait for the first seeds to germinate, for the saplings to grow slowly into trees, and for a mature ecosystem to develop over centuries. This takes a very long time, but in the cyclic model, you're not starting with barren soil. You're starting with a landscape that was already a forest in a previous era. The old trees are gone, but the soil is incredibly rich and fertile, still teeming with the nutrients and the microbial memory of that past life. When you plant new seeds in this soil, they don't grow slowly from scratch. They explode with growth, tapping into that stored history to mature at an astonishing rate. This is what a cyclic universe could provide for galaxy formation. A cosmos already enriched with the gravitational nutrients of a previous cycle. The residual energy and momentum from the previous contraction and bounce would create a universe that is, from its very first moments, primed for rapid structure formation. This inherited head start would act as a catalyst, accelerating the collapse of gas and dark matter into galaxies at a pace that would seem impossibly fast from a standard model perspective. From our viewpoint inside the cycle, we would observe this accelerated early growth and, lacking the context of a cyclical history, we would try to explain it within our one universe model. One way to force our models to match the shocking Webb data is to tweak the influence of dark energy, making it stronger or weaker in the early universe to somehow speed up the process. But what if that tweak is a miscalibration? What if the effect we're attributing to an early influence of dark energy is not the work of a fundamental force at all, but is actually the observable signature of that cosmic inheritance? The unexpected maturity of early galaxies might not be a problem to be solved with dark energy, but a clue that we are seeing the faint, gravitational echo of a universe that came before our own, an ancient rhythm still guiding the growth of the cosmos. Now we venture into one of the most mathematically rigorous and fascinating alternatives to the standard Big Bang paradigm, a framework where the very fabric of reality is composed not of points but of tiny, vibrating strings. This is string gas cosmology, and it emerges directly from the depths of string theory to offer a radically different origin story for our universe, one that naturally incorporates cycles and, in the process, makes the concept of dark energy completely redundant. Unlike the standard model, which requires us to insert a cosmological constant by hand to explain acceleration, string gas cosmology builds a universe from the ground up where the observed expansion is a natural, predicted outcome of its fundamental stringy nature, a direct result of energies and dynamics left over from previous cosmic phases. To grasp how this works, we need to shift our perspective on what the universe is made of. In our everyday experience, we think of the fundamental building blocks as point-like particles, electrons, quarks, and so on. But string theory proposes that at the very smallest scales, these particles are not points at all. They are incredibly tiny, one-dimensional loops or segments of energy strings vibrating at different frequencies. The specific note a string plays determines whether it manifests as an electron, a photon, or a graviton. One of the theory's most profound implications is that it requires extra dimensions of space beyond the three we experience. To be mathematically consistent, string theory needs 9 or 10 spatial dimensions. So where are they? The idea is that these extra dimensions are compactified, or curled up into a space so tiny that they are invisible to us, much like a garden hose looks like a one-dimensional line from a distance, but reveals its second dimension when you look closely. String gas cosmology starts right here with all spatial dimensions, both the large ones we see and the tiny, curled up ones on an equal footing, trapped in a hot, dense, and incredibly small early state. In this model, the universe begins as a chaotic gas of these fundamental strings, all vibrating and moving around, constantly interacting and colliding with one another in a space where no dimension is particularly large. The key to unlocking our three-dimensional reality lies in a special property of strings that point particles don't have. They can wind around the compact dimensions. Imagine one of those tiny, curled-up dimensions is shaped like a circle. A point particle would just sit somewhere on that circle, but a string, because it has length, can wrap around it like a rubber band around a soda can. These are called winding modes, and they play a crucial role. In the early, hot, and small universe, these winding strings effectively lock the dimensions in place, preventing any of them from expanding because the energy cost to stretch a wound string is immense. But as the string gas cools, a monumental transition can occur. Through a process akin to a phase change, like steam condensing into water, the winding strings can annihilate one another. But here's the catch: they can only annihilate effectively if three spatial dimensions are already slightly larger than the others. Once this happens, those three dimensions are freed from the confining pressure of the winding modes and are able to expand rapidly, becoming the vast universe we inhabit. The remaining dimensions stay small and compactified, constrained by their own winding strings. This provides an elegant, string-theoretic explanation for why we live in a three-dimensional universe without needing a separate inflationary epoch. But the story doesn't end there. This framework is inherently cyclic. The expansion driven by the annihilation of winding strings eventually slows. Over cosmological timescales, the expansion could reverse, leading to a contraction where the three large dimensions grow small and hot again. The winding modes reassert their dominance, and the stage is set for a new transition and a new period of expansion, a new cycle. This brings us to the direct link with dark energy. The annihilation of winding strings and the subsequent expansion isn't a perfectly clean process. It leaves behind a residual energy, a kind of echo of those initial confining conditions. Furthermore, the vibrations of the strings themselves, their zero-point energies, contribute to the energy density of the vacuum. In the string gas cosmology framework, these stringy residues from the early, hot phase and from previous cycles don't just vanish. They are woven into the fabric of the expanding universe. This residual energy manifests as a persistent, gentle pressure that acts on spacetime itself. As our three large dimensions continue to expand, this pressure drives a slow, steady acceleration that looks, for all observational purposes, exactly like the effect we attribute to dark energy. The crucial difference is that in this model, no new, unknown substance is required. The acceleration is not caused by a cosmological constant or a quintessence field. It is the natural, predicted consequence of the universe's stringy origins and its cyclical history. The force we call dark energy is, in this view, simply the faint but persistent hum of the universe's fundamental strings, a vibration left over from the process that gave us three dimensions in the first place. What makes string gas cosmology so compelling, beyond its elegant internal consistency, is that it makes testable predictions that differ from the standard model. It predicts specific, subtle signatures in the cosmic microwave background radiation, particularly in the pattern of temperature fluctuations and their polarization. For instance, it predicts a specific and testable deviation from scale invariance in the very small scale fluctuations, a signature that future, ultra-precise SIMBI experiments could potentially detect. It also makes definitive claims about the spectrum of primordial gravitational waves, predicting a much weaker signal from the very early universe than inflationary models do. The ongoing search for these primordial B-mode polarization patterns in the CMB isn't just a test for inflation, it's a direct test for alternatives like string gas cosmology. A failure to detect a strong inflationary gravitational wave signal could be a point in its favor. This ability to make falsifiable predictions elevates string gas cosmology from a purely mathematical curiosity to a serious scientific competitor. It provides a complete, self-contained narrative that explains the universe's dimensionality, its initial conditions, and its current acceleration without ever invoking a mysterious dark energy, instead grounding everything in the dynamics of the universe's most fundamental constituents and the echoes of their cyclical past. But to truly grasp how a multiverse could reshape our understanding of dark energy, we need to step back and consider one of the most profound puzzles in all of science, the concept of fine-tuning. The fundamental constants of our universe, the strength of gravity, the mass of an electron, the strength of the nuclear forces appear to be exquisitely, almost miraculously, calibrated to allow for the existence of complex structures, planets, and life itself. If any of these numbers were even slightly different, the cosmos would be a barren void. Dark energy is the ultimate example of this enigma. Its observed value is positive but incredibly small. If it were significantly larger, the universe would have blown itself apart before the first stars could ever form. If it were zero or negative, the cosmos would have collapsed back in on itself long ago. In a single, lonely universe, this incredible precision feels like a staggering coincidence, a one-in-a-gazillion lottery win that leaves scientists deeply unsettled, as it borders on a metaphysical miracle rather than a scientific explanation. This is where the multiverse concept strides onto the stage, not as a far-fetched fantasy, but as a potential solution to this profound philosophical problem. The idea is that our universe, with its specific set of laws and constants, might not be the only one. It could be just one bubble in a vast, frothing cosmic foam known as the multiverse, where each bubble universe has its own unique, randomly selected physical parameters. In most of these universes, the constants are wrong. They collapse instantly, or they expand into cold, empty voids, or the laws of physics never allow atoms to combine. These are stillborn universes, cosmic dead ends, but in a tiny, tiny fraction of this infinite ensemble, the numbers just happen to fall into the narrow golden window that allows for galaxies, stars, planets, and ultimately, observers like us to emerge. We shouldn't be surprised to find ourselves in such a universe. It's the only type we could possibly inhabit. This is the anthropic principle in action, and it transforms the fine-tuning of dark energy from a miraculous accident into a predictable selection effect. We don't live in a universe with a special value for dark energy. We live in a type of universe that can support life, and that necessarily comes with a value that allows for it. Now, let's weave this multiverse idea into the fabric of a cyclic cosmology, because the combination is where the magic truly happens. Imagine an infinite multiverse where each individual universe is itself cyclic, going through its own series of expansions, contractions, and rebirths. In each cycle within each universe, the specific conditions, the settings for that particular iteration, could be slightly different. The strength of what we perceive as dark energy in one cycle might not be a fixed, eternal constant for that universe, but a transient value set by the specific physics of its last bounce or brain collision. One cycle might have a strong repulsive phase leading to a rapid, sterile expansion. Another cycle in the same universe might have a weaker effect, allowing for a long, fertile period where life can arise. The cycles that are successful, the ones that are long-lived and stable enough to form complex structures and potentially lead to a subsequent bounce, are naturally selected for. They are the ones that persist. In this grand, double-layered scenario of a cyclic multiverse, the value of dark energy we measure is not one lottery win, but two. First, we exist in a specific bubble universe within the multiverse whose fundamental laws allow for cyclic processes to even occur. Second, within that universe, we are living in a specific cycle whose historical parameters, the residual energy from its last rebound, just happen to fall within the life-permitting range. The repulsive force we call dark energy is therefore a double artifact. It's a local phenomenon specific to our cycle within our universe, not a fundamental property of all reality. It's not a universal constant, it's a cosmic circumstance. This framework doesn't just explain why the value is small, it explains why it has the precise value it does. It is the result of a historical process within our cosmic lineage, a value passed down from cycle to cycle, and selected over immeasurable time for its ability to produce a universe capable of looking back and wondering about its own origins. The mystery of dark energy dissolves into a story of cosmic evolution and selection, a tale written not in the fundamental laws of physics, but in the specific history of our own particular corner of the multiverse. After 2 decades of observing the universe's acceleration from a distance, we are on the cusp of a new era, one where we will not just watch the expansion, but will precisely measure its every subtle nuance. This revolutionary leap is being powered by a new generation of astronomical observatories, not perched on mountaintops, but stationed in space and sweeping the entire sky with unprecedented precision. Missions like the European Space Agency's Euclid satellite and the ground-based Vera-C, Rubin Observatory's Legacy Survey of Space and Time, or LSST, are not merely upgraded telescopes. They are cosmic cartographers on an epic scale, designed to create the most detailed 3-dimensional maps of the universe ever attempted. They will chart the positions and motions of billions of galaxies across vast cosmic distances and look back across billions of years, effectively creating a high-resolution movie of the universe's expansion history. Their primary goal is to finally pin down the true nature of dark energy by measuring its so-called equation of state. This term, equation of state, is the key that could unlock the entire mystery. In simple terms, it's a parameter that describes the pressure exerted by dark energy relative to its density. If dark energy is indeed Einstein's cosmological constant, a steady, immutable feature of the vacuum of space, then this equation of state should be exactly -1, and it should remain perfectly constant forever. It would be a fixed, unwavering push from the moment of its dominance to the end of time. This is the clean, simple prediction of the Standard Model. But what if the new data reveals that this number is not -1? What if it shows that the strength of dark energy has been changing over time, however slightly? This would be a monumental discovery, a direct violation of the standard Lambda CDM model that would force a complete and total overhaul of our understanding of the cosmos. It would mean dark energy is not a constant but a dynamic entity, something that evolves and decays, and that single finding would blow the door wide open for alternative explanations. This is precisely where the cyclic universe model moves from a speculative idea to a testable scientific theory. A dynamic, evolving dark energy is not a problem for cyclic cosmology, it is a central prediction. If the repulsive force we observe is not a fundamental constant but a residual energy, the fading echo of a previous cosmic cycle, then we would absolutely expect it to change over time. Think of it like the warmth from a campfire long after the flames have died. Initially, the rocks are very hot, radiating significant heat, but over hours and days that heat dissipates, fading away until it merges with the background temperature. In the cyclic model, the dark energy effect is that residual heat. It was strongest immediately after the bounce that initiated our universe, providing that initial kick to expansion, and it has been very, very slowly dissipating ever since. The equation of state would not be a fixed number. It would be a curve, a gentle slope indicating a force that is gradually losing its potency. This is the falsifiable prediction that sets the cyclic idea apart. The standard model predicts a perfectly flat line for the equation of state. Cyclic models predict a subtle but detectable deviation, a telltale sign of decay. When Euclid and the LSST begin delivering their torrent of data in the coming years, they will be able to measure this parameter with an accuracy never before dreamed possible. They won't just take a single snapshot, they will trace the evolution of dark energy's strength across billions of years of cosmic history. If they find that slightest hint of a slope, that evidence that the repulsive force was ever so slightly stronger in the past than it is today, it will be incredibly powerful evidence that we are not living in a universe with a fundamental dark energy, but in one that is still feeling the aftereffects of its own violent birth from a prior cosmic cycle. The force that is shaping the entire fate of our cosmos would be transformed from a permanent feature into a temporary phase, a passing moment in an infinitely longer and grander cyclical story. After centuries of looking at the universe as a unique, one-time event, we may soon have the first hard date to suggesting we are part of something far older and more magnificent, a single current in an endless cosmic river. And so we arrive at the end of our journey, having ventured through a cosmos far grander and more interconnected than we might have ever imagined. We began with a simple but profound question. What if the very force we thought was driving the universe apart isn't a fundamental entity at all, but a cosmic echo, a memory of events that unfolded in an epoch so ancient it predates our own Big Bang? From the historical shock of its discovery to the tantalizing anomalies in the cosmic microwave background, from the stubborn persistence of the Hubble tension to the revolutionary data from the James Webb Space Telescope, each piece of evidence has invited us to look beyond the standard model. We've explored how quantum fluctuations could be inherited, how information might be preserved across a bounce, and how the vacuum of space itself could be humming with the residual energy of a previous universe. We've seen how cyclic models, from colliding brains to string gas cosmology, don't just offer an alternative to dark energy, they make it completely unnecessary, reframing it as a dynamic byproduct of the universe's own cyclical rhythm of birth, death, and rebirth. This perspective is more than just a clever scientific workaround. It is a profound shift in how we understand our place in the cosmos. It suggests that our universe is not a lonely, one-time event expanding into an endless void, but rather a single note in an infinite symphony, a current in an eternal river of time and space. The force we call dark energy transforms from a mysterious, external driver of our fate into an intimate part of our cosmic heritage, the final, fading sigh of a universe that came before our own. If this is true, it would represent one of the most breathtaking revolutions in the history of human thought, tying together the universe's deepest past and its ultimate future in a single, elegant, and continuous story. It resolves the haunting fine-tuning problems not with a metaphysical shrug, but with a powerful narrative of cosmological evolution and selection across immeasurable spans of time. The beauty of science, however, is that it doesn't end with a compelling story. It demands evidence, and that evidence is now within our grasp. The next few years will be a golden age of cosmology, as missions like Euclid and the Vera C. Rubin Observatory begin to deliver data with unprecedented precision. They will trace the history of the universe's expansion not as a static picture, but as a dynamic film, searching for the slightest hint that dark energy's strength has changed over time. That single finding, a deviation from the perfect constant predicted by the Standard Model, would be the first direct clue that we are indeed living in a cyclical universe, feeling the gentle, dissipating push of a force that is billions of years older than we ever suspected. This is the true excitement of science, the relentless pursuit of a deeper, more beautiful truth. The cosmos is the greatest mystery story ever written, and we are all detectives, piecing together clues from the faint whispers of light and the subtle tremors of space-time. The idea that dark energy is a ghost of cosmic cycles past may well be confirmed, or it may be refined, replaced, or even completely overturned by an even more astonishing revelation. And that is exactly as it should be, so we invite you to reflect on these ideas, to share your own thoughts and questions in the comments below, and to join us as we continue to explore the deepest mysteries of space and time. Remember to subscribe so you don't miss our next journey into the unknown. The universe is vast, strange, and full of wonders waiting to be uncovered. Stay curious.